Right, so I make it 3 minutes past. I always kick off at 3 minutes past, especially on a 9 o'clock lecture. The way I'm going to run this examples class is I'm going to run through some questions, and I think Arthur's just given you an examples sheet last lecture, is that right? And it's called this one. Do you recognise this one? Yeah. So what I'm going to, how many of you have done the questions on it already? No? Okay, well that's good. Because what I thought we'd do is I'd pick out some more of the difficult questions and we'll just work through them together. I'm also going to do a little bit about op-amps because I think you guys don't get enough examples of op-amps. Okay, let's go. So, here's what we're going to do today. I'm going to look at a question which Arthur didn't have time to cover last lecture on the difference amplifier. Then we're going to look at non-inverting amplifiers. Now, you've done inverting amplifiers and you've done various types of op-amp circuits. This is just yet another example of an op-amp, and I'm going to try and bring out some more of the details about op-amps in this question. So, how many of you have seen this in the lab so far? How many of you have gone and done the lab with this bending beam? Okay, so the way these sensors work, so it's basically a strain sensor. It is just a piece of wire wrapped in a coil, and when you bend the coil, so when you bend this sensor here, the resistance of the wire changes effectively, but only by a very, very small amount. You know, if you imagine pulling an iPhone audio cable, the sound quality is not going to change that much. So because the resistance won't change that much. So the point is, when you bend these sensors here, you get very, very small changes in resistance, which you need an op-amp to amplify. And I think Arthur introduced to you last time this circuit. Do you recognise this? Yeah, it looks a bit frightening. But if you do the analysis, what happens is, so here's our op-amp. So let's just look at what we know. Here's our op-amp. Non-inverting input, inverting input, output. Here's our strain gauges. So we've got four resistors, 1, 2, 3, 4, representing our strain gauge, and those are basically on the top and bottom of two parts in the beam to make our bridge. And Arthur derived for you last lecture, or the last lecture on op-amps, this equation that basically says the voltage difference here minus the voltage difference here equals the output here over RF over R1. So I thought just to get you going, I'll give you this little exam type question thing, and it's pretty easy if you've got that formula. So the first thing, you just think about this first one in your head just for a second. Explain why you would need to use an operation amplifier when using a strain gauge. So I'll give you like 5 seconds, 10 seconds to think about it. Then I'll ask somebody to shout out, except you, because you always shout out. Okay, so why would you use an op-amp to amplify the signal coming from a strain gauge? Somebody? Go on. Was that a hand at the back? No? Go on, you look like you're bursting to shout something out.
Because the check resistance is so small.
Exactly. So perfect answer. So 3 marks or whatever you get for the exam. So your strain gauge is attached to an operational amplifier with R1 equals R2 equals 10K, and RG equals RF equals 1 mega ohm. Calculate the output voltage when the Wheatstone bridge produces 0.1 volts across it. So just have a go at tapping those numbers into that formula. Now, so go on. Just bang it into your calculator. There'll be quite a few of these little questions. This is really just to show you how simple, the equations for these circuits can be, and you can analyse them very, very easily. It's not on Moodle yet. I've just written this. Oh, okay. I don't know about that. Yeah, I'll put this on Moodle later, by the way. Come on. Have you got an answer for me? 10. You think? Okay. Well, that's the equation. presumably it's yes, so V1 minus V2 is 10. So the answer is strain gauges produce very small voltages which need to be amplified, and then when you put the values in, you'll get 10 out. Any questions on that? That's just a bit of revision. Any burning questions on any of those circuits? Okay, so we're going to move on to the non-inverting amplifier circuit. So this is a circuit you've not done before. I'm going to teach you something about op-amps as we go along and do this. So you've seen this circuit, which is the non-inverting amplifiers, or the inverting amplifier circuit. And when you put in, so if you put in this signal here, so notice it's positive on the axis, it's positive, negative, positive, negative, positive, negative. When you put this signal into that circuit, what happens is because it's an inverting amplifier, it inverts it. So if you put a positive signal at time 0 in, so positive there, at time 0 you get a negative out. So it's an inverting amplifier. Everything you put into it is inverted. And if this audio system in this lecture theatre had an inverting amplifier, you wouldn't be able to understand me, because every time it would sort of invert my voice, sort of the positive signals would be made negative, so it'd be a bit crazy. So it's very good for sort of instrumentation and doing sort of electronics and things like that, but as a raw amplifier is not amazing. So for this, we're going to, and notice the minus in this gain equation. So the equation relating input to output is RF over R, that should be R in. And notice there's a minus, which means this negative gain, so it inverts. Okay? So the other circuit that you've not met yet is this one, and this is called the non-inverting amplifier circuit. And this is handy because it doesn't invert signals. So this is the type of circuit that one could potentially use for this audio system here, because it will just amplify the voice. It won't invert it. And they're used everywhere. They're a very, very handy piece of circuitry. So if you've got a really small signal you want to amplify, so off a microphone or something like this, you can use a circuit a bit like this. Now, I'm just going to flip between the two of these. So if we go to the inverting, notice the signal here comes in at the negative input, yeah? So there's a positive input op-amp, so non-inverting, and inverting input. And if you look at the non-inverting circuit, you can see the input V in comes into the opposite terminal of the op-amp. So you can see there's our V in here, and it's going into the positive or the non-inverting input. So we've just basically swapped which side the signal's coming into the op-amp. And if you then also go and look at the circuit, so you see, I know Arthur's been teaching about potential dividers, right? Yeah? So if you look at that top bit of the circuit, you can see it's a bit like a potential divider, yeah? And you see it's the centre of the potential divider is going into the negative pin. Well, you see the same type of thing on the non-inverting op-amp. So you've sort of, again, got this potential divider, and it's feeding back some signal. So that's sort of I'm going to show you how to analyse this circuit. It really is incredibly easy. It's much easier than any of the other ones we've analysed. So there's no handouts. So the advantage of this is that if you put in a positive signal, you get a positive signal out. And if you put a negative signal, you get a negative signal out. And I'll put all this on Moodle, so you don't need to scribble it down like crazy. It's not on Moodle yet, because I've just finished writing it. So before we can analyse this op-amp circuit, I need to teach you something about op-amps that's a very, very general thing. And it's just a very simple bit of maths, but it's pretty handy if you come to any circuit analysis. So here's our op-amp, okay? Now we know, so just a simple op-amp, when we know the output voltage is equal to A, which is the open loop gain, times by dV, and dV is the difference between the inverting and the non-inverting input. Okay, so this is like the general formula for the output of an op-amp. The op-amp amplifies the difference in voltage between V plus and V minus. So so I'll just repeat it again. The difference between those two terminals, positive and negative, so dV, is multiplied by A, the open loop gain, and you get your output voltage. Any questions about that? Anybody puzzled? Want me to repeat it? I'm happy to repeat. A bit like a tape player. Very happy. No? Everybody happy? Anybody unhappy? Okay, so indifference. Do shout. Do shout. So we can write this out, this general formula, like we can expand this dV by going A equals V plus minus V minus equals V out, okay? So this is just, again, the difference between those two terminals. So we expanded it out, okay? Then what we can do is so this is very, it's not going to get hard. What we can do is we can bring the A, so this is the open loop gain, over this side, so we've got V out over A. Now, do you remember there was a curve that looked a bit like this? Had frequency and this had gain, and this was a log scale. Do you remember what type of values you got at DC for an op-amp, roughly? What do you think? Anybody got an idea? Guy in the green, what do you think? A million. Huge values, okay? So what type of voltage are you going to run your op-amp on, do you think? What do you think? Roughly, guess. 10, good answer, okay? 10 volts, so so V out, maximum V out is going to be 10, right? And the gain, you say, is a million, okay? So 10 divided by a million is about what? In engineering terms, if you're an engineer? 0, okay? So 10 divided by a million is 0. So we've got 10 here divided by a million. So this is basically 0. So what this tells us is, so we say it's 0. What this says is V plus equals V minus about for an op-amp with lots and lots of gain. So what we can do is when we're analysing these circuits, we can always make the approximation that V minus there is about the same voltage, good enough, as V plus, okay? So for an op-amp with a big gain. So that's a very useful trick when you come to analyse circuits. So we're going to use this in a minute. Any questions on that? Any burning questions? No? Okay, let's use this. So, here's our non-inverting op-amp circuit. Now, what I always tell people to do when they get a question that looks a bit difficult like this is just rearrange the circuit to suit yourself, okay? So if you've got like a complicated resistor network, just redraw it. Like you can keep the wires attached to the same place, but very often, if you just redraw it in a different way, it might look a lot easier to handle. So that's what we're going to do here. We're going to redraw it. So I've redrawn the same circuit. So I've got V out, feedback resistor, R2. Now, what's this remind you of? So if the op-amp wasn't there, and I said, what's V1, could you figure out what V1 was if there was no op-amp there, yeah? Yeah, it's just a potential divider. Pretty easy, right? So, let's ignore the op-amp, it's in grey. So this is a potential divider. There's no handouts. So we can write this equation. We can go V1 is equal to V out times R2 over R2 plus RF, okay? Any questions so far? Shout. If I lose you, please just shout, because it's a really small group this morning, so I'm really happy to do it interactively. Okay, but because this is going to be a question, I've got to ask the question. But I've just proved to you that the negative terminal here is about equal to the positive terminal. Yeah. So what we can do is we can write V1 is equal to V in. Okay. Then we can rearrange it, and we can now just simply get an expression for V out over Vn in, which is the gain of the circuit. So we now know the gain of the op-amp circuit is R2 plus RF over R2. So all I've done, I'll run through it. Who wants me to run through it again? Who doesn't want me to run through it again? One hand. So at the moment you've got 100% of the votes. Anybody wanting to run through it again? No? Okay. Do shout. Do you understand the guy there? You understand everything? Okay, perfect. So, you'll go. I'd like you to design an operational amplifier circuit to give you a gain of, or to amplify a 10 millivolt sinusoidal signal to 1 volt. So I'd like you to design the circuit to do that. So you just need to solve that equation. And I'll give you a clue. It's generally not a brilliant idea to use resistors of like 1 ohm in these type of circuits, because you'll get lots of current flowing around and it'll make the sort of the power usage of the circuit go up. It's also probably not a good idea to use like 10 mega ohm resistors because you won't get any current flowing, and these op amps need a bit of current. So I would pick values in the killer range, so thousands of ohms. Okay, so you've got a free choice, but I'd try and use something, 1 kilo ohm, 10 kilo ohm, that type of value. Have a go. Go on, have a go. And stick your hand up if you've got the answer. Whilst we're doing these questions, it might be worth you just like wandering around, seeing if people are all right. They're going to get a bit. Sorry, yeah, they're going to get a bit. So just wander around. And have you got an answer for me? Sensible answer. Am I looking very confused in the red there, or is that not true? No, not confused. Okay, that's good. So we got. So I just want a value. Some resistors that will give me, if I put 10 millivolts in, I get 1 volt out. So it's just as, and you've got a free choice of you've got to fix either R2 or RF. So you've got to say, well, okay, RF is going to be a kilo ohm, and then you can work out R2. It doesn't matter. You've got sort of free choice components. And very often, when you're sort of designing circuits, you'll have a limited choice of resistors. So, RF might be fixed because you don't have a huge array in your box. Have you got an answer? What you get? You got an answer? 0.1 ohms. That's a bit low, because I said in the kilo. Yeah, so I'd make it like 1,000 more. So if it's it's still not really kilo ohms, is it? Just put a K, call it kilo ohm. So it's 1 kilo ohm, and yeah. Anybody else got an answer? So we could have 100 different answers. Who's got a different answer? I'll ask this man. How are you doing? You got an answer? We get. Oh, okay, not yet. Anybody got an answer? Have you got an answer?
I mean, it's the same representation.
That looks like somebody's getting there. What'd you get?
1 and then 99.
1 and 99 ohms. Okay, so what value did you start off with?
1,000 for R2.
1,000 for R2. Yeah, okay. And that worked out as what? Sorry, 99.
99,000.
Yeah. Okay, so we've got a few answers. So the trick. So I'll just repeat how to do this again. The trick is basically pick one resistor value that's sensible. So pick, say 1 kilo ohm or something, and then say, well, that's fixed, and I'm just going to work out the rest and work out what R2 is. And you've designed already a non-inverting amplifier. So that's how easy these circuits are to design. And you've often got a lot of freedom in your design choices. And interestingly, how do I do for time? Interestingly, if you're designing a circuit with sort of like maybe 100 1 kilo ohm resistors, sorry, I can't talk over you. So if you design a circuit with like 100 1 kilo ohm resistors, it's going to cost you a lot of money to order and you're making thousands of these devices, it's going to cost you a lot of money to sort of order one extra 2 kilo ohm resistor. So very often you'll be sort of limited. If you're ordering a lot of one component, you'll think, oh, okay, well, I'm ordering a lot of those. I'll use that one and see what I have to order as well. So you sort of limit your choice components and it reduces cost. Okay, so I think that's it for op amps. So I'm now going to move on to magnetism. Okay. So what we're going to do is I'm going to do question 2 from this, and then I think we'll have a go at question. So do you feel capable of doing any of these questions on your own yet? If I said go, could you do them all? Could you do them? Maybe. Would you rather I run through bits first? Yeah. Okay. Just tell me. Honestly, I'll do what you want. So if you want to do it on your own, no? Well, okay, I'll run through them. Right, so we'll look at question 2. So this is what's in question 2. So I always like to draw a picture of what's going on first. And it says calculate the flux density in the air gaps. So calculate the flux density there, and calculate the lifting force of the magnet. So I'm going to try and go through this really, really slowly, and we'll then do the next one together. So, has Arthur taught you about these analogies to magnetic circuits? Has Arthur taught you about these analogies to magnetic circuits? Has he? Or is he just no? Yes? What was the answer? I heard an answer there.
Yes.
He has. Right. Okay. So whenever I draw out, because I'm an electrical engineer, whenever I draw a magnet, I instantly draw a magnetic circuit, and I sort of pretend it's an electrical circuit because I'm much more comfortable with these than I am with these. So here's my sort of analogous circuit. You can think of these sort of bits of metal as effectively the wires of the circuit. Okay, so they've got no resistance, or no magnetic resistance. You can think of these air gaps as effectively the resistors of the magnetic circuit. Okay, and this coil you can always think of as like a current source. So here's a battery I've got as my current source. So I just always draw this because it makes me feel much more comfortable than looking at this. And I suggest you do too. And then what I do is I label everything just to make me feel even more comfortable. So I go, here's a resistor, give it an R. Here's another resistor, give it another R. And we've got a phi for magnetic current flux. And we know, because Arthur's told us, N times I is how much magnetic current the coil is going to generate. And I is the current you're going to put into the coil, and N is the number of turns. So the more turns you have, the more flux is generated in the circuit. Okay? Everybody happy with that? Any questions? Nope. You don't have to write this out. I will put this on Moodle. It's just not on Moodle now because I've just finished writing it. So, yeah. I'm videoing too, by the way. I tried to video last examples class, and it didn't work because the camera up there is rubbish, and I just had like 1 pixel for the board. So I brought my own. So I'm going to try and upload this to the internet later. So hopefully that'll be easy for you to revise off if you want to. So there's our circuit in big. So again, just write in what I know. So write in. So we know the values of these magnetic resistances, and it's R is equal to L, which is the length of the air gap. Mu0 is the permeability of free space, so with less T's than permittivity. R is the sort of the relative permittivity of the medium. So if you've got various materials have different permeabilities, and also interestingly, so at this stage you're just doing this with sort of DC magnetic field. So the magnetic field is basically stationary. When you look at materials in frequency domains, when you sort of try having magnetic fields changing at like megahertz or kilohertz, this value of mu r changes a lot as a function of whatever frequency. We don't need to worry about that. And A is like the cross section of your material or your magnetic circuit. So we've got our resistances, we've got our current flux that's being generated. So we can now write there's no notes. We can now write the equation for the there's no notes. Sorry, can you? No. Yeah, so now we can write our equation for our magnetic circuit. So this you think about. So if this was like a normal circuit, you could think of this as V, or like the driving force, because it's like the the sort of magnetic force that's being generated. This is the current, effectively. So this would be the I in a normal circuit, and this would be the resistance. So you can think of this as V equals IR, but of course it's magnetic. So that's just like how I like to think of it. Any questions so far? Any questions? Okay, so Arthur's first question was, calculate the magnetic flux density. Now, can you see the magnetic flux density in this equation? Can you see it? Have a look, have a stare. You don't have to shout out. No. So the answer is no, you can't see the magnetic flux density. But what we can see is A, which is the area of our circuit, and we can see phi, which is the magnetic flux, not the magnetic flux density. But we know the magnetic flux density, B, is related to the magnetic flux phi over A, because like flux density is, it's going to clearly be flux divided by area. So we can replace the phi and the A with a B. With a B, there we go. And we can solve Arthur's first question, or whichever it was. Where are we? This is it. So calculate the flux density in the air gaps. So we've now got an equation that will do this. So we've got L, I, So size of the air gap, current in the coil, number of turns, and permeability of free space, which is 1. Do I do it? Yeah. So that's it. So I'm not going to put the numbers. You got a question, guys?
This is question 3 on the exercise.
Yeah. Well, I've called it. He's misnumbered it because this is actually exercise sheet 12 question, and then we've got question 6.1. So it doesn't even match up. So anyway, you're going to have to. I'm sure you'll figure this out, right? Yeah, so I'm not going to plug the numbers into that, but that's the equation and the strategy you go to tackle it. Any questions on that? Nope. Okay. And the next bit was calculate the lifting force. So I've sort of rearranged this equation. It's because it sort of reminds me a bit of kinetic energy equals half mv squared, because there's a half in it and there's a squared, and that's the force. So that's the lifting force of our magnet. And we've got B, because we've just calculated. We've got A, we've got mu0. We can solve this, so that would be another 3 or 4 marks. So that's how to tackle that question. I'm now going to do one with you where you can have a little play. You got any questions on that? Okay. So, am I going to do this one next? Which one should I do next? I think we'll skip this one. That's a bit. So we'll move on to the last question I'm going to do. So this is sort of an equivalent. This is some type of. This is question 6.5. He's labelled it. 6.5. Sorry.
We have only 5 questions.
Well, let me see your sheet. I think I might have the sheet from. Yes. No, 6.5. This is called. Yeah, it's the same number. Yeah. So look, it looks like this. Yeah. Yeah. Okay. So this is basically, although it might not look like it, this is basically the same question. And this is sort of a classical electromagnetic question you'd set electrical engineers. And what he's got some type of electromagnet. It's sort of electromagnet you might find to keep a door open of a computer room or something like that, or some type of latch that's an electrical latch. And he's got this sort of a magnetic circuit here, and he's made the problem a bit more difficult because this time he's got like an air gap that can move. So he's got like this bar that can slide in and out. And he's going to ask you various questions about it. So I know it looks scary, but what we can sort of pull out of this picture is, again, we've got our source of magnetic flux, so our phi. So that's like our V in our circuit. That's like the driving flux. This sort of metal bit we can think of as effectively the wires to our circuit, so it's going to have no magnetic resistance. And the only other thing that's a bit different is we've got this air gap. We've had an air gap before, but now we've also got a piece of plastic in here as well. Well, plastic is just like air really, and it's got a permeability of 1. So really, you can think of this as air as well, okay? Because it's got the same the magnetic properties of plastic are about the same as air. So in fact, it's sort of the same question as before. So again, draw turn our circuit that we're quite uncomfortable with into something that we're comfortable with, or at least I'm comfortable with, and label it. So we've got Ni here is producing our magnetic flux, so that's this. We've got, now I've put in 2 resistors here, so this resistor here represents this air gap, and this resistor here represents this plastic piece here, and that's it really. It's sort of exactly the same as the last question really. So then I just wrote the equations. So I said the resistance of this is equal to the length of the air gap divided by permeability, relative permeability of air divided by A. Then this resistance is equal to length of plastic over the permeability of free space divided by relative permittivity of plastic divided by the area. So, yeah, so I don't know if it... Are you guys writing because it helps you remember, or are you writing... You're writing to help you remember. Is that okay? Because I always like to sit back in lectures and not write anything and just focus on what. So do as you like. This will all be online with the video. But we know the permeability of plastic is the same as the permeability of air, which is 1. So we've got the same question as last time, basically. So we can write our equation for our magnetic circuit. So we've got the driving force, so you can think of this as like V, or the voltage in an electrical circuit. You can think of this as the current, and you think of this as the resistance. Okay, so we've got effectively when you're thinking about this in terms of like an analogy to electrical circuits, voltage equals current times resistance, and we've got N. We've got I think we've been given I can't remember. We've got the length of the air gap. We've got all these values. So just pop it in, and we're sorted. There we go. So what did he ask you? Magnetic flux density. We don't have magnetic. He wanted the magnetic flux density, which is B, but we don't have B in that equation. But we know B equals phi over A, so we can just replace phi over A with B, and then we can get B, which is the magnetic flux density, out. Okay. Was that it? It can't be it, can it? No. Okay, so what I'd like you to do is I would like you to have a go at this one. Okay? So I've drawn a picture for you already, and this is much simpler because actually there's no. Anyway, just have a go at it. Have a go at this one. And there's no. Yes. So what he wants to start, in fact, I'll tell you what, no, we'll work through this step by step. I broke it up so we can have a go. So we've got I'll explain it, then we'll do bits together. I'll stop talking, and I've forgotten your name, I'm sorry. Henry. Yeah, so we're both here to help you. If you've got questions, we'll answer lab questions. So we've got about 20 minutes to just general questions. If you've got no more questions, you can go. If you've got detailed questions, put your hand up, whatever. Yeah? So.